Okay, we're recording now. Good. So again, the question posed on Moodle forum was, why does it take n times to create n copies? So if it takes one time unit to create one copy of an item on SDFS, and we want to create n copies of the item, why does it take n time units to do it when we do it in parallel? And why does it not take n time units when we do it in a pipeline? So there is a constraint to be kept in consideration here, and that constraint is that every computer has an upper limit to the bandwidth you can use, right? So when I was saying last time, when your network card connects to the local switch, it negotiates its connection mode and speed. Most of the times, the connection mode will be full duplex, meaning that you can send and receive at full speed in both directions. And let's say that the negotiated bandwidth is 1 gigabit per second. Okay. What this means is that you can send data out at a maximum rate of 1 gigabit per second. If you initiate 2 transfers, then these 2 transfers will need to sum up to 1 gigabit per second, meaning that each of those transfers will now be able to transfer at only half of the maximum bandwidth, right? If you have n of those transfers happening in parallel, each one of those will be able to take 1/n of the available bandwidth, on average, of course, right? And that's why it takes n time units to create n copies when those copies are done in parallel. Okay. Now, when we do it in a pipeline, what happens is that the client who sends the data to the first data node can send the data at full speed, at the full bandwidth, let's say 1 gigabit per second. The data node that receives it can receive it, assuming it has no other data to transfer at that point, it can receive that at full speed because it's a full duplex communication, as we said. And as soon as it receives the first few bytes of that stream, it can start sending the data out to the second data node, again at full speed, right? Remember, since this is full duplex, I can receive at full speed and send at full speed. Okay, so in the time it takes for me to send, in that one time unit, it takes me to send my first copy to the first data node. That first data node has also transferred most of that copy to the second data node. And the second node has transferred most of that copy to the third data node. So that's why the overall time is not n time units, but 1 plus change. Okay. There was another question about NewSQL as big data storage. I will not address that question now. There's a couple of points, a couple of good points in that question, but I'll prefer to leave it for later on when we cover NoSQL stores. Right, that's a better time to discuss NewSQL stores and CDWs and so on. Okay. So that's that out of the way. So let's then focus on today's lecture. Let me share my screen. This guy. Okay. So hopefully you should be able to see my slides full screen now. Okay. Let me see. Okay, I'm looking at the questions on Slido. The teacher is sharing the PowerPoint now. I wasn't sharing anything until now. The following quizzes will end at 6 p.m. every Wednesday. Yes, that seems to be something that works for everybody. Okay, and now there is a question about, I guess, MapReduce, and let's keep that question on the side because I think we will cover it anyway as part of today's lecture. Okay. If we haven't addressed it by the end of this lecture, please let me know and transfer that question over to the forum, and I'll try to address it there. Okay. So today is all about distributing processing. Okay. So if we take a step back and look at ways we can write programs, like programming models, we can write a traditional program. Traditionally, programming is serial, meaning that there is one thread of execution. That one thread goes through the data in some order, process it, and produce the result. But these days we have many cores, we have many computers, so it's obvious that we can parallelize, and we should parallelize. So let's parallelize. But that said, there are many questions to be answered. Right? How do we do it? So it's time for some brainstorming here, because there are many problems to solve. Right? Whenever we want to parallelize the processing of anything, the way to do it is we take that something, that anything, and we partition it to workers. So how do we partition the input to workers? What are the partitioning criteria? Yeah, and who decides how to partition? That's the first question. Once we have, let's say, decided that, then how do we distribute the work to workers? Assuming we have our big input, we've split it into n components, one for each worker. How do we give it to the workers? I mean, physically, do we put it somewhere where they take it? Do we send it over the wire to some place? Exactly what is the mechanism? And once those workers have finished their processing and they have the results, how do we aggregate these results? Right? How do we bring everything back from the workers to the one place where we want to see the result? And utterly, how do we synchronize and orchestrate the workers? We need to have something in place that decides all of the above and that runs this scenario through the worker. So decides how to split data, lets workers know, distributes the work to workers, lets workers know, waits for the workers to finish their processing, then aggregates the results, and everything in between, because things can go wrong, right? Workers might fail, the input might be incorrect, parts of the output might be missing for whatever reason. So all of these problems we now need to solve. Okay, so let's start with thinking about this problem and the solution to this problem when we have only one machine. Right? That's a single computer, and we have many cores or many threads running on these cores. So let's think about parallel programming for many cores and threads on a single computer. So what's the first thing that comes to mind, right? It's exactly this approach I said. So you take your input, you break it into parts that can be processed concurrently, and then you execute them concurrently across your cores and your threads. Okay. Now, what are the problems and the challenges here? First of all, we need to identify the parts of the input or the task that can be processed concurrently. And this is not always easy, as we will see in a few seconds. So the exact partitioning scheme is quite important, because the way we split the tasks to workers also dictates to a big extent the time it will take the workers to process their task. Ideally, since we are parallelizing, we would like all of the workers to finish at roughly the same time. Or to put it in different terms, we would like all of the tasks to be of roughly the same complexity. And as we will see, this is not easy to always achieve. Coordination is something that we need to keep in mind. As I was saying, who decides what happens where, and who keeps track of the computation. And then depending on how the data is shared across my workers, synchronization becomes important. So I'll get, there was a question on slide, I'll get to it in a minute. Right, so if, for example, the input, sorry, if the output is in a shared location, or if the place where we store intermediate results is in a shared location, I mean shared across workers, then we need to make sure that workers do not step on each other's feet. So we need to synchronize them somehow. But then once we introduce synchronization, whatever we synchronize on becomes a point of contention, something that everybody is racing to acquire. Say it's a lock or something like that. Everybody is racing to acquire that lock, and a lot of the threads that try to do the processing end up waiting just to acquire that lock. There are ways around this, but that's something we need to keep in mind and we need to solve. Result merging, as I said earlier, once the workers have finished their processing, we need to have a way of merging the results. And what this also means is that the results need to be expressed in a way that allows merging. We will see some examples shortly. But even before we solve any of these problems, we need to answer the question, does it actually make sense to do it? So you may be familiar with Amdahl's law. Amdahl's law tells us that if we have a computation to perform, we can look at the computation and divide it into parts that can be parallelized and parts that cannot be parallelized. In the optimal scenario, the parts that can be parallelized can be reduced to take 0 time. So, assuming we have infinite resources, we can spawn an infinite number of threads, and each thread will take one part of that parallel computation, and so that the time it takes to process it would be minimized, practically 0. But then the overall time to process that task is defined by the part of the task that is serial, right? So if we have a task where a large part of its processing is serial, why bother parallelizing it? That's the key insight here. And even if we can parallelize a big part of it, how parallel can we go? Yeah. Yes, job schedulers like PBS, Pro, and Slurm do these things. That is correct. But here we're talking about designing something from scratch. So what we're trying to do is to design something like PBS and Slurm and what have you. Right. Someone asked for a syllabus, topics covered. A rough syllabus was in the slides for the first lecture. If you want a more detailed syllabus, I could produce one. But I think what you're asking for was in that first lecture slides and also in the course catalog entry for the course. Okay. All right. So, and all of this, what we've been discussing so far applies to the single computer case. Now, wait till we go distributed, because then we will have more problems to solve. So here is a question for you. What is the best way to parallelize a job on a single machine using multiple threads and cores? And this is a poll slide that will go live now. And the options depend on whether my threads can access the input and or intermediate data from a shared memory location or a thread local memory location. Okay. Option A says everything is shared, so the input and intermediate data is at a shared memory location. Option B says that we send each thread a full copy of the input data, and then the thread uses its own memory for intermediate data. Option C says we send each thread only part of the input data, probably the part that it needs to process, and then it uses its own memory for intermediate data. And option 4 is that the thread chooses what part of the input data to process, assuming that the input is in a shared location. It then goes and accesses it and uses a shared location for intermediate data too, right? So what do you think makes the best sense here? Okay. So on Slido, most people seem to go for option D. Okay, so I think I'll stop the poll in maybe 10 seconds if you want to get your answer in, and then we'll discuss this a bit. Okay, 5, 4, 3, 2, 1. Right. Okay. So stopping the poll. Is there any way of seeing the results? Okay. Right. So there are votes for all 4 options, right? So let's start with that. The least preferred option is option B, which says it's fair to send the full copy of the input data and uses some memory for intermediate data. Could one of the people who have voted it down, so didn't pick it, tell me why they think it's a bad option? Write on Slido or unmute yourself and say so.
Probably because it uses up too much memory, redundancy.
Okay, that's a good one. So I'll try and rephrase the answer of your classmate here. Option B says we send a full copy of the input data. So that means every thread will have that full copy. So we'll copy around the data as many times as there are threads. Data copying is actually quite expensive. It's one of the things you probably want to avoid, not just because of the memory it takes, but also because of the time it takes to create the copies. There are things that are hidden to the user. So even if you do a mem copy, you probably want the copy of the data to be close to the core where your thread will run. So you need to think of details such as pinning my thread to a specific core. Is the core on the same socket as where the data lives in RAM, and so on and so forth. So that full copy can be quite costly, right? The next option up in popularity is option A, which says each thread accesses the input and intermediate data at a shared memory location. So again, I'll ask for the people who didn't select this. If one of you could tell me why you think this is a bad idea. Right, so we're talking about option, what was it, A now, right? So the problem with option B was we do all of these copies and this is expensive. So option A has no copies whatsoever. Doesn't this solve the problem? So people on Slido talk about deadlocks and mixing the resources and processes, deadlocks, competition. Yes. So all of this is actually what we go for. Yeah. So all these threads access the input and intermediate data to certain memory location, meaning that if actually the problem is not when we try to read the data. There are some complications there again regarding memory locality and so on, but I'll just brush through them. I'll ignore them, sorry. But the problem appears when we write the data. Yeah. So someone says there is no distribution and we need coordination. So in all of these cases, we need coordination. And the distribution would come from the fact that each thread would access, I guess, part of the input or whatever part is assigned to that thread. Yeah. So there's still distribution here for some definition of distribution, and there's still coordination, as in all other cases. But the problem is what quite a few of you mentioned there, that this requires synchronization. We need to synchronize across our threads. And as we said a few minutes ago, this synchronization can be costly. Okay. So the next option up in popularity is option C. Each thread is sent a full copy or of part of the input and uses its own memory for intermediate data. Okay. So what's wrong with this? What do you think is wrong with option C here? And I mean, I'll try to say this thing. That the problem with option A was that we need synchronization when we write the output. Now, option C says that every thread uses its own memory to write its output. So there's no synchronization required there to write the output. And since we sent a copy of part of the input to the thread, we don't incur the big cost to read it, right? Okay. The answers that come in Slido are, I mean, I'll just mention them. So someone has to decide optimal division of work. That is actually true in all 4 cases. Someone needs to do the division of work anyway. We're talking about multiple threads going through this input. The assumption is that someone has done the division or the partitioning and knows what goes to which thread. So one of the costs here, one of the key components of the cost is this copying here. Even if we copy part of the input, right? Even if we copy only the partition of the input that each thread needs to process, at the end of the day, we are creating a full copy of the input partition across threads. So it would be nice if we could alleviate that copying. There is also the added cost of aggregating the intermediate results. Yes. So as someone says there, it would be better if we can keep intermediate data in some shared memory. The complication with keeping it in shared memory is that we then need to mediate or synchronize the access to that shared memory. So we're back in option A if we do that. Someone mentions network costs. Remember, this is on a single machine, so there is no network cost per se. There is memory copying cost though. Okay, and then okay, I mean all of this makes sense. And let's look at option D, which is the most popular one in the poll. And here we say that it chooses what part of the input data to process. We assume, as I said earlier, that the thread will access that data from a shared location, and then it will use a shared location for intermediate data. This is just like option A, only the decision of what part of the input to process is taken by the thread and not by some mastermind. Okay. So those of you who did not choose this option, why do you think this is bad? What's wrong with this? Mm-hmm. So the fact that there is no single coordinator means that all threads need to talk to each other to make sure there is no overlap. And how do you do it then? Yeah. So right, a couple of answers coming in there. So the bottom line here is indeed, as you have guessed, that for the threads to decide and to reach a consensus on what each thread will process, they need to synchronize, right? So we know we need, since the output is in a shared location, we know we need synchronization for the output. But now we have also introduced a requirement for synchronization for the input. Okay. So all of these options, they have their pros and their cons. Okay. What is the best way to parallelize a job? I mean, is there a single correct answer? Now that we've gone through all of them, what do you think? Is there a single correct answer? So what I'll do is I'll duplicate that poll and run it again. So now that we've gone through this discussion, can you please pick again what you think is the best option there? Okay, I'll wait for another maybe 5 seconds here for any last minute answers. 3, 2, 1. Okay. And I'll stop the poll. Right. So let me see what happened then in comparison to the first time we had the poll was actually probably not much changed, which is not what I was hoping we would do. So the support for the first option dropped. Support for the third option rise. Pretty much everybody who opted for the fourth option the first time opted for the fourth option this time again. So I'll take away 2 messages from this, right? First message is there is no single optimal way. And the way in which we would choose at any time is we would look at, we would need to look at the access patterns and the problem itself, and whether we can properly parallelize it, whether we can pre-compute the size of the output so that, or the size of the intermediate data for each thread, so that we can have a shared location without the need for synchronization. There's many things to be taken into account. But I'll also say this thing, that in the case of MapReduce, which is what we will be discussing in a few minutes, the option that the designers went for is actually option, option C and D together, right? So each thread, or actually A and C. So each thread is assigned a part of the input by the mastermind, and that part of the input is in a shared location. But then each thread, or each worker, as we should call them for MapReduce, uses its own memory location for intermediate data. Okay, and we'll see what this means in a minute. Where's my thing here? Okay, so let's have a look at some examples here. Okay, let's say we want to lowercase all letters in a very large text file. Okay, this is a very easy case. Why is this easy? So this is easy because data can be partitioned in equal size partitions. We can pre-compute the number of partitions very easily. We can pre-partition the data very easily because we don't care about things that might be on partition boundaries. Okay, we want to lowercase all letters. All we care for is that every partition has roughly the same number of letters. If we assume that the file is in ASCII, we can just partition by about byte boundaries. Say the file is that many bytes long. I want to create that many partitions. So every partition should be whatever the size of the file is divided by the number of partitions. Excellent. And then we are sort of guaranteed that each worker will receive the same amount of work because each worker will have the same number of letters to lowercase. So we can partition the data very easily, and there is no dependency within or across partition. We can process each partition independently of others. Okay, so either we have our worker, either we have the file in a shared location and we give our workers byte boundaries. So worker 0 will take bytes from 0 to 10. Worker 1 will take from 11 to 20. Worker 2 from 21 to 30, and so on. Or we send this data to the workers. I mean, it's the same. The key characteristic here is that each one of those workers can go through their partition and do their processing without worrying what other workers are doing. Okay, and since the output is of a known size, we can pre-allocate an output file, and each worker can directly write its output to that partition of the output file. Again, no synchronization needed on the output. So this is amenable to a simple master worker solution. The master pre-splits the input. It assigns each of these splits to worker, and then sort of gathers the results. And each worker, what needs to do is receives a split, goes through each split of the input file, and returns the results to the master or writes the results to the output, as we said. Okay. Now, what happens if a worker dies mid-processing? Right. Why this could happen? Let's say that there's something wrong in the input, like there is a character in the file that is not an ASCII character and cannot be lowercase, and the worker was not prepared to deal with this situation. So a worker dies. What happens then? In order to address this situation, we need the master to monitor each of the workers, or all of the workers, and B, for the master to perhaps spawn a new worker to handle the part of the input that was assigned to that failed worker. There might be more things to do here. If the worker failed because the input is bad, then someone needs to go through the input and clean it, or someone needs to take the decision that that part of the input is not processable, I will ignore it. Okay. What happens if the master dies mid-processing? So what this means is that we can no longer detect errors of the workers, but given this, we can split this situation in two cases. A, all of the workers continue and finish successfully. B, one or more of the workers die, right? So if one or more of the workers die and we don't have a master, then the output will be garbled. Yeah. But if all of the workers continue and finish, there is a chance that the computation is, it can't be saved, right? So if all of the workers go through their split and write their output to this location they need to write their output to, then at the end of all of the workers, we have the output there. The problem is, how can we know, right? If the master has died, how can we know that everything processed and proceeded as planned? Yeah. So let's go for a somewhat more complicated case, a not so easy case. Let's say we want to lowercase only the first letter of each word in this very large text file. Not all the letters, but just the first letter of every word. Why is this not so easy, right? So the first problem here is that data can't necessarily be partitioned in equal size partitions. So think of taking your file and splitting it in equally sized chunks. And then there is this word that is across partitions. It begins at the end of one partition and continues into the beginning of the next partition. What would the workers do, right? The worker that processes the first partition will see that word, will uppercase or lowercase its first letter, and then go to the end of the file and terminate. Good. The worker that works on the second partition will now see something at the beginning of the partition. It wouldn't know it's part of the word. So what it will try and do is it will try to lowercase the first letter of that, but then that output would be wrong. So someone says, why not split to an equal number of words in this partition? That's an excellent suggestion. So this addresses this. How can we fix this while maintaining the simplicity of the master worker solution? And the answer is, let's split to an equal number of words, or actually not exactly equal number of words. Let's discuss that. Equal number of words might lead to an unbalanced partitioning, because some partition could be a lucky partition and have small words, and some other partition could be an unlucky partition and have big words. And then the two partitions would be of unequal size. What we could do is, let's say, if we end up splitting the file at the middle of a word, then we move the partitioning boundary to the end of the word or to the beginning of the word. So we make sure that words are never split across partitions. And moving this boundary is easily done by the master. And just stick about, like, read backwards or read forwards until you find the end or the beginning of the word. Right? So this is something we can solve, okay, in this simple case. Now, the question is, can we parallelize this step? So do we actually need the master to do it, or can we parallelize it? And if we parallelize it, how can we orchestrate this parallel computation, right? Why would or wouldn't we want to parallelize this step? So this goes back to the discussion we had earlier. If we parallelize this step, that means we need to spawn multiple threads to do it. That means these multiple threads will be going through the same input, and that means that they would be writing to a shared output. So there might be the need for synchronization. Okay, and does it make sense to do so? So how many partitions do we have? If the number of partitions is not that big, then a single thread can quite well do it, and the time we would gain by spawning multiple threads to do it would not be worth it. Okay. Right. And again, we have to solve the other two questions. What happens if a worker dies mid-processing? What happens if the master dies mid-processing? Okay. Let's think of a somewhat harder case. So let's say we have a large graph, and this graph is in the form of a series of text lines. Each line contains the ID of a node, and then a list of IDs to which this node has outlinks, out edges. Yeah. And we want now to compute how many intlinks each node has, how many edges point to that node. So in essence, what we want to do is to take this file and compute its, let's say, inverse. We have a file that lists outlinks, and we want to compute inlinks, right? Why is this harder than the previous case? Well, of course, data can't necessarily be partitioned in equal size partitions, because there is no guarantee that each of these nodes has the same size of its adjacency. So some nodes will have way more outlinks than others, right? If you think of this as a social graph, some people will have way more, will follow way more accounts than others. If you think of this as a web graph, some web pages will be having way more hyperlinks to other pages than some other pages. Yeah. So the equal size partition becomes a bit more complicated now. It's not just a matter of find a word, find a split point and then move forward or backwards until you reach a word limit, a word boundary. Now you need to compute the split point and then move forward or backward until you reach the beginning or end of an adjacency like this, of a line in this case. But then you need to keep in mind that it might be, you probably want to do both. Probably want to skip both forwards and backwards and choose the split that is more balanced. Okay. But now data across partitions is also not necessarily independent. Outlinks in one partition will reference a node that might be in another partition. And what is actually the problem here is that outlinks for multiple partitions need to be aggregated to compute the final result. So there might be nodes in all of the partitions I have that have an outlink to my single node, right? And you can think of this as consider a very popular person in a social network or a very popular web page on the web. And let's assume that all other people on the social network or all other pages on the web actually point to that one page, right? To compute the inlinks of that one page, we will need information from all partitions. So now we can no longer just look at one partition at a time. So if we have a worker and that worker looks at that one partition, we can no longer say that's the output of the worker and that's the output of the computation. We now need to aggregate the intermediate results to compute the final result. So how can we fix this while maintaining the simplicity of the master worker solution? Right? Again, how do we partition the input? How do we distribute the work? How do we aggregate the results? And what happens if one of the components dies mid-processing? You see that we have a not so difficult problem, and things have become more complicated quite quickly. Yeah. First level link or second level link is also allowed. I guess what you mean is, are we looking for one hop away or two hops away? I think that's what you mean by the question on Slido. I would say that in this case, we just want one hop away. Okay. So for the partitioning, we can go with what we said just a few minutes ago. So we split the input in equal sizes, byte-wise, and then we skip forwards or backwards until we reach the end of a line or of an adjacency. Okay, and we can do both and pick the partitioning that is the more balanced. How do we distribute the work? We can do whatever we were doing so far. So we give the partitions, the boundaries to the workers, and the workers just create the input from the shared location. But how do we aggregate the results now? Right? So it's no longer possible for each worker to have its own dedicated output in the final output. So what we will need is that each worker writes its output to a local location, and then we aggregate. Or if we want to share the output, then we will need to synchronize the workers, which is something we definitely, or not definitely, probably we want to avoid. Okay. Okay, we'll see an example of this in a few minutes, because that's the archetypical example for MapReduce. Let's look at an even harder case. So let's say we have a large number of I think I'll need to address this question. Quite a few people have asked for the answers to the slides. So the answers are, whenever there is a definitive answer, we mention the answer in the lecture. Whenever we do not mention an answer, that means there is no single right answer. And we need to consider all of the cases and all of the trade-offs to find it. Okay. So in quizzes or polls earlier on, whenever there was a right answer, then the final PowerPoint and PDF has that answer highlighted in red. But what is important for me is that you understand the discussion that's going on here. Just knowing the answer is of little value. Okay. What I would like you to understand is how we reach that answer. Okay. Yes, I'll try to provide notes. I'll try to provide notes for the lectures. But the notes won't be as detailed as the discussion we have here. You're probably much better off going through the lectures or taking notes during the lectures and then asking questions on the forum. Okay. I will provide notes. It's just that, as I said, probably your notes would be much better because they would be tailored to you. And then if you don't understand something, feel free to ask the question on Moodle or on Slido during the lecture, of course. So one of your classmates says they are unable to visualize the previous question. We'll touch upon it again because, as I said, it's the archetypical example of MapReduce. So let's go back to this even harder case here. So here we have two-dimensional points. So a file that has a bunch of x and y coordinates, x and y pairs, and we want to compute simple clustering into k clusters. Those of you who have taken machine learning courses, what we're going for here is k-means. Okay, the easiest of the clustering algorithms. And the gist of it is that you have your points. You take k of those points. You probably pick randomly, or you pick the first k or whatever. And those points become your cluster heads. So each one of those points now is the leader of one of your k clusters. What you do then is you go through all of your points in your data set. And for each one of those, you compute the distance to all cluster heads. And you pick the one cluster head, which is the closest to your point. And once you've done that, you assign that point to that cluster. Okay. So in the simple case where we have only two clusters, I pick 2 points in the space. These become the cluster heads. And then I go through all other points. And for each point, I say, okay, this new point, is it closer to cluster head A or cluster head B? Let's say it's closer to cluster head A. Good. So now this point is assumed to be in the cluster of cluster head A. Yeah. And I do it for all of my points. Once I've gone through all of the points, what I do is I look at all of the points that are in a cluster and I average them. So I average their x coordinates, I average their y coordinates, and this gives me a new virtual point in the cluster. And since this is the average of everything in the cluster, it's at the, let's say we can assume it's at the middle of the cluster. Right? So it's a virtual point that has the minimum distance to the points, to the remaining points in the cluster. Not exactly, but bear with me. So now this new point becomes the new cluster head. We do this for all the clusters. And then the next step is we try to compute the distance of the new cluster head to the old cluster head. Try to see how much our cluster heads have moved. Okay. And if the maximum movement is below some threshold, then I stop. Otherwise, I loop again. So I go again through all of my points, again compute their distance to the closest new cluster head. Again, I assign them to the cluster. I average them out in the end and compute new cluster heads, compute the distance to the previous cluster heads, and then either terminate or loop again. Okay. Why is this problem then harder than the previous ones? Again, data can't necessarily be partitioned in equal-sized partitions. For this simple example, that's probably not the case. There might be situations where this is actually true, depending on how the coordinates are stored in the file. So if it's a text file, then we need to worry about like breaking coordinates across boundaries. But the key problems here are that data across partitions is not necessarily independent. So if I take just one partition, I won't be able to know what all of the cluster heads are across all other partitions. I'll need to somehow know all cluster heads, right? The algorithm requires multiple passes to terminate. I need to go through step 1 for all of my points. I need to go through step 2 practically for all of my points again. And then I need to somehow synchronize to compute the computation of step 3, and then do it again, right? So whenever we deal with big data, this doing it again can become a major cost factor. We don't want to go through our data more than once if we can. Not always possible, depending on the algorithm, but if we can minimize the number of passes, then that's good for us. How can we fix this while maintaining the simplicity of the master workers approach, right? How do we partition the input? We address that. How do we distribute the work? We've addressed that, right? So we'll just do whatever we were doing so far. But how do we aggregate the results? Now this has become way more complicated now, because we need to, computing the average of all points for step 2 is a bit complicated, not that much. But to compute step 3, we need to aggregate over the aggregates to compute the new cluster heads and the new distances. So this becomes somewhat more complicated still. Yeah. And again, we need to solve all of the problems of what the worker dies, what if the master dies, and so on. There are situations where we don't care for a master's workers architecture. So everything we've discussed so far has assumed that there is a mastermind who pre-computes the partitions and knows how to distribute the work and so on. That's not always the case. Although for MapReduce, which is what we will be discussing in the second hour of the lecture, we do have a mastermind. We do have a master and a number of workers. Okay. We will discuss masterless architectures in the future when we go over Dynamo and Cassandra. But for now, assume there is a master, but think what would happen or how the discussion would change if there was no master. So a classmate asks, why not take equal size partitions and cluster separately and then merge sequentially to create larger and larger clusters? It's not that easy. Yes, so it's not that easy. Why? Because at every point you need to be able to assign points to clusters, and then you need to be able to average the cluster heads. Okay, and to average the cluster heads, you need to maintain sums and counts, like sums of x coordinates and counts of x coordinates, sum of y coordinates and counts of y coordinates. And there are situations where maintaining these sums may not be practical. In any case, you would need to have all of that and then gather all of that information from your workers to compute the final cluster hits. Yeah. Okay. So there will be the need to have this aggregation step. I think what your classmate there goes for, the exact comment says, why not take equal sized partitions and cluster separately and then merge sequentially to create larger and larger clusters? That's not far from what we would do with MapReduce. But what you allude to is the need for this aggregation step. Okay. And how you do the aggregation then becomes something you need to think twice about. Okay. And now for something completely different. So let's say we now have many computers, not just many cores or many threads on one computer. We have many computers on a local network, like a cluster or a data center. We need to answer all of the questions we were answering so far, right? So how do we partition the input? How do we distribute the work? How do we aggregate the results? What happens if a worker or the master dies mid-processing? Only now we have more headaches, right? Because now we have the network in the middle. So what happens if the network goes down across the workers? Or what happens if the network goes down between the master and one or more of the workers? What happens if the network goes down between workers and where the input or the output is? And all of these questions, or the answers to all of these questions, change depending on the point in the computation where this happens. Okay, it's a different thing to lose network connectivity when you're reading the input, and it's a different thing to lose it when you are actually computing stuff, right? In one case, it hurts, in the other, it doesn't. Network outages are often transient. So you might lose network for an amount of time, and the network comes back afterwards. So what do you do then? Do you kill off the worker if the worker loses connectivity, or do you wait for the network to come back? And if you wait, how long do you need to wait for, right? From the point of view of the master, if the master loses connectivity to a worker for X seconds, should it assume that worker is dead, or should it assume that something is temporarily wrong? And in either case, what should the master do, right? These are all questions we now need to answer, and there's way more what ifs, right? What if part of my shared storage is lost? What part of my shared output is lost? And so on and so forth. So if we were to write code to actually address all of this, we would be in for the time of our lives. It would take a long time to solve all of these questions, solve all of these problems in a good way. There are ways out there. I mean, there are systems out there that have been used for computations like this. So as the simplest case, we could have shared storage in the form of NFS, a network file system. And then we have multiple computers that mount that NFS, so they can now remotely access the same shared network storage. And what I can do is I can run a script that logs into my worker computers remotely, spins up processors, scripts there that go through the input, and so on and so forth. So I can, I am the mastermind. I decide how the input is split, and I hard code those splits into my scripts that I run on the different computers, and so on and so forth. That works, but of course it's not ideal because I'm a human. I might be doing things wrongly, and even if I've done everything correctly, things might go wrong of their own volition. The network might go down, a disk might fail, the power might go out, and so on. And I'm not, as a human, quick enough to react to these situations in real time. There is then the batch synchronous parallel model. We will discuss it more in a few minutes. And there are other ways to do this. So there is OpenMP and MPI. There is parallel virtual machines. There is MOSIX. There are Beowulf clusters. All of these, actually, these four here, are quite frequently found in high performance computing settings. The main difference with what we try to do now is that in HPC settings, you sort of assume your computing nodes to be reliable, right? They are all under the administration of your usually very adept administration team. You monitor them very, very carefully. You don't expect to lose machines mid-computation, or even if you do, you don't expect this to be the norm. Whereas in our case, with clusters that are in the order of tens of thousands of commodity computers, we've said in the past that you can assume failures will happen mid-computation. Okay, so that is what's wrong with these options. The first one is too complicated for the human. Options 3, 4, 5, 6, and so on work, but they make specific assumptions on the infrastructure, and these assumptions do not apply in the setting we are considering now. And the batch synchronous parallel model is something that we will discuss in a minute. Okay, and then fault tolerance in this large-scale environment becomes the big headache, because fault tolerance means we need to have methods of detecting failures and methods of responding to these failures and fixing them in real time. Okay, so we'll take a short break here, maybe a 5-minute break, like stretch your legs, get something to drink, and then we'll go dive into MapReduce and how MapReduce does stuff. Okay, so see you in 5 minutes, so 12:10. Okay, good. So let's resume then. So let's see what MapReduce does for all of these problems that we were discussing. We'll start with a brief introduction to MapReduce. So why MapReduce? Where does the name come from? Actually, the terms come from Lisp. The way they are applied in Lisp is you have this map and reduce concepts. The map concept is that you have a list of values and a function, and map will apply that function to all of the values. So given a list of values as the input and a function, you produce a list of values in the output, each of these values being the outcome of that function applied to an element of the input. And then there is the reduce concept here, where again, you have a list of values and a function, and the output is, you can think of it as a single value that has been computed by combining all of the values in your input list using the reduce function. Okay. Now, MapReduce, the term, is used for like different things. Like, so you can use MapReduce to denote the programming paradigm, the idea of using a map and a reduce function in the way we will see shortly, but it is also used to denote implementations of the model. So there is the Google MapReduce implementation, there is the Hadoop MapReduce, there are other MapReduce implementations out there too. Okay. Now, for a short history, this whole thing started back in 2003 for the public. That's when Google published their Google FS paper. We went over HDFS and Google FS last week. And then the year after that, they published a paper on their MapReduce system. That's when Doug Cutting, who you may know as the person behind Lucene, he found that a really interesting idea and started incorporating MapReduce and Google FS into Nudge. Nudge is what later on became Lucene. A couple of years down the line, and Google FS, or HDFS, and MapReduce was factored out of Nudge and became its own thing called Apache Hadoop. By the way, the joke here goes that Hadoop, you may know how the logo of Hadoop is a little elephant. The name Hadoop and the elephant came from the kid of one of the developers of Hadoop, and that kid had a toy elephant whose name was Hadoop, right? Anyway, so in 2007, there were only 3 companies that were like officially using Hadoop. But then 2008, Hadoop version 2 is born. Hadoop version 2 will cover it next week, and it was addressing some of the shortcomings of Hadoop version 1. That's also when Yahoo announces that it uses Hadoop to build its web index, and up until recently, Yahoo was the entity with the largest Hadoop cluster around. Okay. By that time, 20 companies are using Hadoop officially. 2008 is when Hadoop wins the Terasol challenge, actually blowing the previous winner out of the water. And so it started rising in popularity. 2012 is when Hadoop version 1 became available. So Hadoop became sort of like stable. 2013, Yarn, so Hadoop version 2, is deployed in production at Yahoo. 2013 is when Hadoop 2.2 became available. These are, like key releases in the lifetime of Hadoop. 2017 is when Hadoop 3 became available, addressing some of the shortcomings of Hadoop 2. And these days we're in Hadoop 3.3 something, so still in that major version. Right. So let's revisit the problem we saw in the very first lecture. And let's say we have a dataset consisting of all the lyrics in the world, let's say, right? We have one file per song with the lyrics for that song, and then the verses are in lines in this file. This is a text file, okay? One verse per line, and let's say that we can access this file as a sort of virtual key value store, right? So the key is the line number, and the value is whatever is the text of that line. And what we want to do is we want to compute all unique words and their frequency of appearance, which is the word count problem we discussed in the very first lecture. Yeah. So we would like the output of this computation to be a list of distinct words. And for each of these distinct words, the numbers, the frequency of its appearance. So how many times we find that word in not just one file, but across all files. Okay. Right. So this is how we do it with MapReduce. Keep in mind we have these map and reduce functions here. Yeah. Right. So the map function, takes as input a key and a value and produces 0, 1, or more key value pairs at its output, right? And the reduce function takes a key and all of the values that are associated with that key and produces 0, 1, or more key value pairs at its output. There is an implied complication here, and that is that in between a map and a reduce, you take the output of the mapper and you need to group it by key so that you end up with something that looks like this, a key and all of the values with that key across all mappers you had, all map invocations you did previously. Okay, and let's take, oh, by the way, anyone knows where these lyrics are from? Don't Google it. It's not important. Anyway, so let's look at an example here, right? So for this word count, yes, two people knew it. Good. That's 2 more than last year. Okay, good. So let's say that this is the map function. So what we do here is, remember, we take a key value pair, the key being the line number, the value being the line, the string, like the text of the line. And for each word in the line, I produce a key value pair, which is that word translated to lowercase, and the value is 1. Okay. So assuming that this is my input, like that one line from there, I take this and I translate this value to this bunch of key values. So and lowercase and being the key, value of 1, the value of 1, ship value of 1, blah, 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 right? All the way through my input. What happens then is that this output across all map invocations I might have, and I might be able to do this like in an embarrassingly parallel manner, right? Assuming I have partitioned my file properly, as we were discussing so far, I can have multiple mappers going through these different partitions and producing lists like this. What I need to do then is group all of this output by key so that I end up with something like this: albatross and 1, and then 1, 1, 1. Like there's three values, and there's 1 value from this occurrence of end, 1 value from this occurrence of end, and 1 value from this occurrence of end. Yeah, so 3 values there, and so on. And then I'll do my reduce. And what my reduce does, it expects to see a word being the key and a bunch of counts being the values. And what it will do is it will sum up all of the counts, right? And then it will produce 1 key value pair at its output, and that will be the word plus the sum. So this here now becomes this, like albatross 1, and we'll aggregate these 3 values and end up with 3, and so on and so forth. Okay. Someone asks on Slido whether there is an option to use Python programming for big data. Yes, you can, but would you want to? That's a different question, right? Depends on what are your selection criteria. I mean, if you want to go for complete and utter performance, probably Python is not what you want to do. It's a little bit different for Spark, but also for Spark, writing your code in Java or Scala will be faster. Like the computation will be faster than if writing it in Python. Yes, there should be a difference in execution times with Scala and PySpark. I can't give you a blanket answer because it depends on what you do in the Python part of the code. If you do text manipulation there, then you're much better off doing it in Scala or Java. Okay, just to address this, the main reason why Python ends up being slower is that the framework itself, so Hadoop, MapReduce, or Spark, is written in Scala, right? Sorry, Java or Scala. So Python can only understand or cannot understand the binary representation that Hadoop or Spark uses internally. So every time you need to cross the boundary between Python and Java or Scala, what happens in the background is that your data is translated from whatever your framework uses to whatever Python understands. And this translation can take a long time, right? So depending on how many times you do it and what exactly you do in your Python code, this may or may not be a big cost factor. Okay, so that's the gist of MapReduce, or at least the MapReduce paradigm. But now let's move on to discuss the MapReduce system, right? So at a high level, the key idea of MapReduce is to try and move the computation to the data and not the data to the computation. Okay, what is this now? What do we mean by this? We mean that if your data lives somewhere on your big cluster and you want to do something on a partition of that data, you probably want to execute that piece of processing close to where your data lives, if possible, on the same node where the data is stored. So remember how last time we were talking about data nodes? If your partitioning is, let's say, one block of a file that lives, and you have one replica of that block on some data node, you want ideally to execute your processing for that block on the data node, right? It's not always possible, it's not always a good idea, but from the point of view of performance, that's what you would ideally want to be able to do. And the way you do it is that this mastermind that decides how things are split and who does what tries to assign the processing of tasks to machines that are closer to where the data lives. Okay. Again, if possible, co-located with the data on the same node as where the data lives. With MapReduce, we have the following main entities. We have the master. The master is sometimes also called the job tracker. Then we have a master per worker. So we have a single guy that looks at the whole cluster. That's the job tracker. And then for every computing node, you have a local master, which is also called task tracker. And then for every node, in every node, you can spawn multiple workers. And these workers are called tasks. Okay. And then, of course, you have the client that initiates this big job. By default, your input and your output is HDFS. So you assume your input data to be a file or a directory or whatever on HDFS. And the final output of your computation will also be stored on HDFS. But intermediate data, so the output of mappers, for example, is not stored on HDFS. It's stored locally on the local disk, on the local file system of whatever machine computed the map function. Okay, and I have this in red because in a couple of weeks we will be discussing Spark, and this is actually one of the key differences of Spark, because Spark has also the option of storing intermediate results in memory, not on disk, as is the case with this. Okay. People in the past have asked me, what if I do store on the local file system, but the local file system is actually a memory mounted device? So I have allocated part of my memory and have mounted it as a directory on the local file system, and that's where I store my results. Isn't that the same as what Spark does? The answer is no, for reasons that we will discuss when we cover Spark. Okay. So this is sort of pulling everything together. Remember, we had HDFS up until now. What was the role of the task tracker? the task tracker keeps track of the workers on one node and is responsible for reporting back to the job tracker. So perhaps it will become clearer with this picture here. Yeah. So up until today, we knew about HDFS or Google FS. So we had the name node, the single mastermind for the distributed file system. And then we had data nodes running on my worker nodes. And the name node daemon, the name node process would communicate with the data node processes for the various tasks. Okay. And then each one of these has its local file system with its local disks and whatnot. Now we go and add the MapReduce part of this. And the MapReduce has its job tracker, which is the single mastermind across the whole cluster. And then per node, a task tracker, right? So this is the mastermind for what happens in this node alone. Because later on, we will go and spawn multiple workers, multiple processes or threads in this node, and someone needs to take care of them, like look after them. That's a task tracker. Okay. And you will see how in this picture, the task tracker and the data node are sort of shown as being on the same node. Yeah. As I said previously, this is ideal because now I can say this part of my computation needs to read data that lives in this data node. So I will give it to this task tracker so that the task that is spawned from there, the thread or process, runs on this node. So it accesses data that's only local and doesn't need to transfer data over the network at all. Okay. Oh, and by the way, yes, these are called worker nodes. So this figure was, the original Hadoop or MapReduce paper figure. We don't refer to these nodes as slave nodes anymore. We refer to these as worker nodes. Okay. Okay. So what are the phases through which a MapReduce job execution goes? First of all, we have the job submission page, and this is where the client creates a configuration object and does some more things that it needs to do. We'll see what these are. And then it has this package that is a job, and this job is submitted to the job tracker. Okay. The job tracker needs to do stuff on its own to initialize the job. So it needs to allocate space in its internal data structures, decide a bunch of things like how to schedule things across my cluster. It needs to look at which of the computing nodes have space to take more computation, and so on and so forth. So this is the initialization step. We'll see it again in a couple of minutes. The next step is that the job tracker needs to schedule map tasks. So it needs to look at the computation that was sent to it from the client, see what needs to be done for the map tasks, decide how many map tasks need to be executed and where they need to be executed, and then finally submit those tasks to the task trackers to be executed. Next step is the execution of the map task locally at every task tracker node. And then remember that we need to be able to group the intermediate output before we go to the reduce stage. Yeah, we said that a few minutes ago that the output of the mappers need to be grouped by key. And eventually we will need to be able to do this grouping across all mappers. And the easiest way to facilitate this, or the most efficient way to facilitate this, is to sort the output by that key, because then I can go through my output in key order and decide and merge it across my mappers. We will see how it happens. It's not exactly like that, but we will see how it happens, right? So for the time being, keep this in mind, that the intermediate output is sorted and stored on the local disk of the mappers. Once this happens, the job tracker is informed, and then it needs to schedule the reduce tasks. So again, it needs to look at the job description, see or compute how many reduce tasks are needed, decide which nodes will execute those reduce tasks, and then send them to the local task trackers for execution. The reduce tasks are executed, and then the output of the reducers needs to be again sort of stored on HDFS. Yeah. Once all of the reduced tasks have been finished, the job tracker is informed and the job completes. Okay, these are the key steps. On the side, job trackers and task trackers monitor the progress and the status of the job. So the task tracker monitors the tasks that are executed locally. So whatever processes or threads it has spawned to execute the tasks. And every now and then it will inform the job tracker of that progress. And then what the job tracker does is it monitors progress and status of everything across all the task trackers. So it knows exactly like how much of the input has been processed globally, how much of the output has been, or I mean, not exactly how much, but how far into the computation of the reduce phase the reducers are, and so on and so forth. So this is a high-level view. So we have our input as a file or more files on HDFS. I'll address that question shortly, right? So this file is split into what we call input splits. And this is a virtual splitting. So what the input split has is actually the boundaries. So input split 0 is from byte whatever to byte whatever of my HDFS file. Yeah. Then each input split is assigned to a mapper. The mapper goes through the input split, so it goes and reads the data that is in its input split, applies the map function to it, and produces the output. Okay. The output of the mapper is firstly written in memory, and then sorted in memory and stored on disk. And when the mapper finishes, just before the control is passed over to the job tracker to initiate the reducers, the map itself, or the map side of the computation, will do a like a sort merge join. It will go through all of the small sorted files it has produced on its local disk and will merge them into one big sorted file. Okay. Yeah, so there is this question of intermediate output sorting is part of map task or reduce task. So it's both sides do something like that, and we will see why, right? The mapper needs to have its output merged and sorted locally, but then when the reducer wants to compute stuff, it needs to do a global merging. So it needs to go through the pre-sorted outputs of the mappers and fetch them and sort them and merge them, and then compute the reduce function. Okay. So we can assume that the mapper output then is sorted at this stage. Okay, sorted by key. And then the reduce phase kicks in next. And in the reduce phase, what will happen is that the reducers would go and fetch parts of the output of every mapper, and what part they will fetch, that is decided by that mastermind that has assigned the reduce task. So the reduce task has something similar to the input split, but this specification specifies only what part of the output of the mappers each reducer will process. So the reducers fetch those parts and merge them into one file, and then this file is fed to the reducer function, and that produces the reducer output, which is finally written on HDFS. Okay. The mapper output is stored, is actually buffered in memory, not exactly stored. So you have a buffer. As your mapper function goes through the input, it produces its key value pairs in the output, and these are stored in a buffer in memory. When this buffer is full, what happens is that you freeze it, you create a new buffer to be filled in with the additional outputs, and this frozen buffer now you sort it and you store it on disk. Okay. So that storing of the buffer is not part of the critical path. But when or if you execute a MapReduce job of your own, you will see that this process of merging the output, like doing the sort merge join on the actually this external sorting. So those of you who have taken IDSS or database systems, you've seen this algorithm as external sorting. Yeah. You have many small sorted files, and then you merge them in pairs. You merge the output in pairs and the output in pairs, or if not in pairs, in groups, until you have one big sorted file. Yeah, and that one big sorted file per mapper is stored locally on the local disk of the mapper. Okay. There is a very interesting question here that says, if intermediate data is stored locally, how is it fetched in a way that it isn't costly? That's a very good question. So what happens here? I mean, we will probably discuss it again in a couple of minutes. What happens here is that when the map task is executed, we already know how many reducers we will have, because that's part of the job specification. So the mastermind knows how many reducers there will be, and it also knows, or it can compute, what keys will be assigned to each reducer. Not exactly. We will see in a couple of minutes that there is a way for us to define how the keys produced by the mappers are grouped to produce the input to the reducers. And the mappers know that. So what they do, what happens here is when I do this sort merge, I sort the keys so that keys that are to be assigned to the same reducer are stored next to each other in the big sorted file. Okay. So my mapper output will consist of a big sorted file, but sorted so that everything in, say, this first part of the file is to be processed by a single reducer. Everything in the second part of the file is to be processed by a single other reducer, and so on and so forth. Yeah. And so when the reducers want to fetch their data, they are given a location, they are given the IDs of task trackers where their input lies, and they will go to that task tracker and request only part of the file, part of the mapper output file, and that is the part that is related to them. And they will do this in parallel. They will go to all task trackers and fetch everything in parallel. These two steps are the most time-consuming steps in MapReduce usually. The sort merge, the local sort merge, especially if the output of the mapper is big, and then the global sort merge, because you need to fetch data over the network. This is the shuffle phase, and this is, as I said, this is probably the most expensive part of this computation, but it's not something you can really alleviate. Okay. When this sort happens on the mapper side, we don't need to move data across mappers. But when the reducers do the merge, they need to fetch data from multiple mappers to produce even one input to the reduce function, right? So here is when the transfer happens, the reduce side. There's a couple of added components here that we haven't addressed. So let's see. The steps we need to take are, of course, parse and split the input. We need to execute the map function. We need to be able to partition and sort the intermediate results. Then the results are transferred to the reducers. Actually, it's the reducers that go and fetch the results. It's not the mappers that send the results to the reducers. The reducers fetch the results instead. Then the reduce function is executed after this sort merge. And finally, the output is stored on HDFS or wherever. Okay. And as programmers of MapReduce, as users of MapReduce, we have the power to define each one of these steps. Okay. So the input parsing and splitting is defined by something called the input format. The input format defines how the input data is to be split, how the input data is to be read, like buffered or unbuffered or whatever, how it is to be parsed, and so on. There is a bunch of built-in input formats that work for 99% of the time. But there is 1% of the time where we need to do something that's trickier, and then we need to define our own input format, okay, or tweak the built-in ones. For the map function execution, there is actually, these are names of Java classes. I should have said this. So there is a Java class called input format, or an interface rather. Where is the class? I think it's a class, by the way. Sorry. There is a Java class called input format, and then subclasses of input format for different types of input format. There is a Java class called mapper, whose methods we can overload to write our own map functions. The intermediate result here, the partitioning and the sorting, there is something called the group comparator. That's the actual name of the group. The actual name of the Java class is something like group comparator. I can't exactly remember now off the top of my head. I can look it up if you want. So we can define how keys are grouped. We can define how these keys are then assigned to reducers by something called the partitioner. And there is this thing here called the combiner. I'll get to it in a minute. Okay. The intermediate data transfer to reducers happens during this shuffle phase, as someone mentioned on Slido. Again, I'll need this to be clear. It's the reducers that fetch data. It's not the mappers that send, right? There is a reason behind this. The reason is that if you allow mappers to send data to reducers, that transfer might be in vain because something might happen in the map phase, and some other mapper fails, and then the computation needs to be restarted, or the reducer. There's also a performance point to be made here, because what the reducer does is it fetches these files from the different mappers, and it sort merges them in main memory and writes the output on disk, and then does an external sorting as we've seen it in the database or IDSS course. And it's more efficient to do it while the reducer is fetching data as opposed to the mapper sending the data. So fault tolerance and performance reasons. Then there's the reducer function execution. And actually here, there is a class called reducer whose methods we can override to define how the reducer, what the reducer does. And then how the data is stored on its DFS in the end is defined by another class called output format and its subclasses for different types of output format. There is a question here: how do we decide how many mappers and reducer threads we need? I'll answer that in a minute, right? So I want to address this combiner first. So when these guys implemented MapReduce, design and implement MapReduce, what they observed was that there are many cases where the output of the mapper contains multiple occurrences of the same key. Right? And what will happen in the next phase is that I will sort these keys, merge them, and then reduce them. But wouldn't it make sense if I could run like part of the reduction, part of the reducer function here on the mapper side? So that's what the combiner does. The combiner is like a mini reducer. Actually, if you look at the combiner class signature, you will see that the methods it exposes are actually the same as the methods of the reducer. Okay, the combiner is just a mini reducer, and it's a mini reducer that is computed, that is executed before the mapper output, before that buffer is written to disk, and while the sort merge or the external sorting happens on the map side, and then possibly also again when the merge sort or the external sort happens on the reduce side. As programmers, we can define or not define the combiner. Even if we define a combiner, there is no guarantee that the system will actually use it. So MapReduce has some internal logic that tries to decide whether it makes sense to use the combiner or not. Okay. This is one of the very common mistakes we often see with people who write MapReduce code for the first time. And that is that they write their mapper to produce some key value pairs in the output. They write a combiner that merges part of that output. And then they write a reducer that expects to see the merged output of the combiner, but the combiner is not guaranteed to be executed. So if you have a combiner, make sure that your reducer can handle both combined and uncombined input. Okay. So how do we decide how many mappers or reducers do we need? That is like the million-dollar question. The default policy for the mappers is that I want as many mappers as there are blocks in my file. Yes, where are we touching LFS versus SDFS in the picture? Well, I will explain that, sure. So by default, the input is split in block boundaries or close to block boundaries, right? What happens is that the default input format, so like input format, text input format, and so on, the input formats we usually use for processing text files, which is what we do most of the time, splits the input at block boundaries. And if we have an input format that cares for words, for example, doesn't want to split words, is it will take the block as a boundary and then like seek back or forth until it reaches the end or the beginning of the word, and that's the split point. Okay, so that word that is in the boundary will be processed by only one mapper. So this is where we read stuff from SDFS. Yeah, so we touch SDFS when the mappers want to read their input. We also touch SDFS in another place where I'll explain shortly. But in this picture, we touch SDFS when we read the input. We touch SDFS when we write the final output. But everything else in here is on the local file system. So the output of the mapper is written on the local file system of the mapper. The sort merged input of the reducer is written in the local file system of the reducer, right? And that's it. Okay. Right. So for the number of mappers, usually, as I was saying, that was defined by the number of blocks in the input file. The number of reducers is trickier to compute. So what happens is that the system sort of trusts the programmer to tell it how many reducers it should use. Hadoop installations come with a default value for number of reducers. And if the programmer, or I mean, the user of Hadoop does not define anything, the system will go with that default. Typically, it's one, or you have only one reducer. The dotted lines are there to denote the splits between mappers and reducers and so on. Yeah. So this is reducer. Sorry, this is mapper. This is reducer. This input split we'll see in a minute what it is. It's not actually, it's not the mappers who compute this. Having as many mappers as we have reducers. So we will see next time. Next time we will discuss MapReduce version 2, and we will go over some recipes of how you would use MapReduce to process different problems. Sometimes you want just one reducer. Sometimes you don't care. You would go for as many reducers as you could use, and then you would want the number of reducers to be a small multiple of the number of processing nodes that you have. Yeah. Going for number of mappers equals number of reducers is just another arbitrary number for how many reducers you need. Typically, you would want the system to adapt to the load and spawn more reducers or fewer reducers. But that's very difficult. Why is it so difficult to adjust the number of reducers? Can you guess? So I'll just say the answer in the interest of time. Yes, it needs to be orchestrated from the start. Remember how the mapper needs to know what are the reducers, or how many reducers and what keys are assigned to every reducer in order to store the file appropriately. That's not easily done if we can fluctuate the number of reducers. It's not impossible. It's not just not easily done. Okay. So this is the anatomy of a job execution. We have the client being a Java program that we write as the MapReduce users. So it's a Java program, and in it has a MapReduce program written in Java. At some point in our program, so if you look at the structure of a code that implements MapReduce, you will see that it starts by creating a configuration object and then fills that configuration object in. It defines where the input comes from, where the output will go, what the input format is, what the partition is, what the grouping comparator is, and so on and so forth. And then it packages that up in a in this object that is then serialized, given to the job client, and at some point, my code will want to submit it, right? So going through the code on the client side line by line, at some point, I'm creating a job. And when I do it, what the job client does is it will communicate with the job tracker to get a new job ID. Okay. Then given this job ID, it will take its configuration object and it will copy it to some shared directory on HDFS. It copies it to HDFS so that all task trackers, all computing nodes will be able to access it from that one location. Okay. But as part of doing it, as part of computing this configuration file, what the client does is it also computes the splits, right? So remember this figure? I said that this input split computation is not part of the mapper. That's because the input splits are actually computed here by the client. Okay, so the configuration that is copied to HDFS contains all of these like input format, blah, 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 blah. But the split or the algorithm to do the split is predefined by the client. Okay. And once this is done, we can then go and submit the job. So submitting the job lets the job tracker know that I've copied my configuration in that one location. So the job tracker will pull it, will initialize its internal data structures, and then it will go and compute input splits or retrieve the input splits. And by doing so, it will know now how many mappers it will need to spawn, how many map tasks. The next step is to go and actually compute those map tasks, like schedule those map tasks. Now, this is a pattern here that we've seen with HDFS as well. Instead of the job tracker reaching out to the task trackers, or instead, I mean, last week we were saying, instead of the name node reaching out to the data nodes, what happens is that the name node just waits there. The data nodes heartbeat every now and then to the name node. And in this case, the task trackers heartbeat every now and then to the job tracker. Heartbeating means that in fixed periods of time, or every now and then, in the general case, the task tracker or the data node will send a report to the job tracker. And this report will contain things such as what is the current progress of the map and reduce tasks, how many resources I have available, exactly which tasks I am executing, and so on and so forth. And that the response to that heartbeat is the chance that the job tracker or the name node has to send anything to its friend here. Yeah. Okay, so the job tracker sits there and waits for task trackers to heartbeat. And every time a task tracker responds by saying that, you know, I have that many map tasks, that many reduced tasks,
and I have space for that many more, then the job tracker will decide which of the map or reduce task of this job to assign to this task tracker, and will send the message back as a response to the heartbeat. The task tracker will then take the specification of the map or reduce task that was assigned to it, will retrieve the resources, the specifications, the configurations from HDFS, and then it will launch a child JVM in which the map or reduce task will be executed. Okay. And it will be monitoring the health and progress of this task. And every now and then it will be heartbeating back to the job tracker with its reports on the progress. Okay. The lectures will be until week 10, not until week 5. I'm not sure why you. Someone asked whether the lectures will be only until week 5. No, until week 10. Sorry, you'll be seeing more of me. Okay. So task assignment. So the job tracker assigns each task to a task tracker. How does the job tracker know which task tracker is idle? It knows that because every time the task tracker heartbeats the job tracker, it sends over a report of its status. You know, how many, as I said, how many tasks I'm executing, how many more tasks I can take on. This was not in the Google paper, actually. This is something that was done by the Hadoop MapReduce people. And the reason here being that the Google architecture is a little bit different. And the assumptions that the Google guys did for their infrastructure is a little bit different to what we can make practically for where Hadoop is being used. Then how does the job tracker decide which task to run where? Okay, there are two things it needs to take into account. I think one is, are there resources for me to spawn that task on that task tracker? Okay, are there free slots for a mapper or a reducer? The second thing is that task tracker close to where the data lives? Okay, remember we try to transfer the computation to the data. So if I now have a new MapReduce job and I see I need to spawn like 10 mappers, and the task tracker heartbeats and says, you know, I have an empty slot for a mapper, give me a map to execute. The job tracker will try and see which of the blocks or which of the partitions of the input file are stored on the same node as where that task tracker is executed. And then it will assign that computation to that task tracker. And this is how the computation is transferred to the data. Okay. Now, on top of that, that's what data local, write local, and remote refer to here. When I manage to schedule a map, so a task where the data lives, then that task is said to be data local. If I cannot do that, then the next best thing I can do is assign it to a node that is in the same rack, and then that's rack local. And if that's not possible either, then there's no other option than going remote. So assign the task to some task tracker where the mappers will need to then fetch the data over the network, as opposed to over the network through multiple hops, as opposed to reading it locally or reading it from some other node in the same rack. Okay. Now, this being a scheduler also needs to decide how different MapReduce jobs are intertwined in time. So if I have multiple MapReduce jobs, all of them want to spawn mappers, for example, what I can do is like FIFO, where I spawn all of the mappers of the first job, wait for them to finish, spawn all of the reducers of the first job, wait for them to finish, and then go to the second job. Or I can try to be a bit smarter, such as, if I have only one job, give it all of the map slots available. But if I have a second job waiting, as the map slots of the first job become available again, instead of executing more map tasks for the first job, I will start executing map tasks for the second job up until the point where the cluster is balanced between the two, right? And capacity is something that's close to that too. But then there is also something called speculative execution. And what this is, oh, I think the time is 1 o'clock. I'll just say this one and then stop for today, and I'll see you again next week. So speculative execution is an idea where if a map task or a reduced task is taking too long, the job tracker will spawn a copy of that task or multiple copies of that task in other task trackers, and whoever finishes first wins. Okay, and this is to address situations where a single node might be overloaded or where a single node might be having some issues. The downside of this being that the computation that we do, the code that we write, needs to be able to handle cases like this. So it needs to not make assumptions that a map or reduced task is executed only once. Okay, we will see some repercussions of this with Spark too, because Spark also has speculative execution, and there's more to be discussed there. Okay, so we'll stop here for the day and continue next week. If you have any questions, please feel free to post them on Moodle. I'll upload the complete version of today's lecture slides on Moodle too shortly. And yeah, looking forward to seeing you next week again, or to answering your questions on Moodle. Thank you.
Thank you.
Thank you, Professor.
Thank you, Professor.
Thank you.